presentation we start with piezo-electric materials for simultaneous energy harvesting and sensing. Please.
Okay. First of all, thank you so much, Igor, for inviting me here. It's always such a pleasure to be in Italy. And second, I would like to thank my colleagues from University of New South Wales who worked on this project. We are an interdisciplinary team. I come from the area of computational mechanics, so all the numerical modeling and optimization that I will be showing today is my area. Mary comes from the structural health monitoring. Mahbub comes from the computer science, and his specialization is machine learning and deep learning. And Patricio here is the PhD student who did all the work, so he's at the intersection of all disciplines, so he didn't have the choice. Yeah. The motivation for this work comes from the IoT sector, where the power supply for sensor nodes is recognized as one of the main challenges in its development. And as you know, the majority of sensors are powered by batteries, which means that first of all, their service life is limited by the life of a battery. They need replacement, they need maintenance. And here are a few numbers for Australia. It is expected to, the IoT market is expected to reach 25 billion Australian dollars by 2024. And by 2025, we are expected in the whole world, we are expected to have about 50 billion of IoT devices, which create a huge problem of the battery waste, because of course all this battery needs to be recycled, that they need to be utilized somehow. And all these challenges, they bring forth the necessity to explore alternative sources of energy, among which we are looking at the piezo-electric energy harvesters as one of the possibilities to convert mechanical energy into useful electrical energy. And particularly, we are interested in structural health monitoring because, again, it's in high demand, as particularly in Australia, over 70% of all bridges, they were built before 1980s, and now they are reaching the end of their lifespan, and therefore they need to be continuously monitored. So imagine you have a bridge, and every time a vehicle passes over a bridge, the bridge will vibrate. And the goal is to create a pH system that will convert this vibration into a useful voltage. Then this voltage produced by the pH can be supplied to a sensor, partially to a processor and transceiver, which is used to send the data to the cloud. And that's how a conventional IoT system looks like. However, if we look again at this picture, then the voltage signal, which is produced by a pH, contains the information about the source of vibration. For example, mass and speed of the vehicle that passed over the bridge and produced that vibration. So what if we can solve this inverse problem? What if we can use the voltage directly to sense the environment? For example, the traffic characteristics. Then if we go back here, we don't need a dedicated sensor, because we can use the same piece of hardware, the same pH, as both as energy harvester and a sensor. In this way, the data will go directly to the processor and sent to the cloud, and the power will be distributed more efficiently, because we will not have a sensor. And that means that we will have a lighter, energy efficient, less battery dependent, and easier to maintain system, which we call simultaneously energy harvesting and sensing SEHS system. So if we want to design a harvester for such an application, then we have to worry about both objectives. We have to make it efficient for energy harvesting and for sensing, to work as a sensor. So here is a basic model that I will be talking about. The energy harvester is modeled as this composite plate made of the substructure and two layers of the piezoelectric material. it's attached to a vibrating base. In our case, it will be a bridge. So this whole thing vibrates, and the voltage is generated. So that's another look of the same very simple model that we start with. It does not have to be rectangular. In fact, we can use any shape in the XY plane, and we will try to optimize it. Then we can look at more interesting configurations. For example, this one is very popular in the literature, where we have a beam with some resonators attached to it. And we can look at even more interesting configuration. For example, this one. The idea is very similar. That's a plate which consists of unit cells which have this shape, which represent a mass on a beam. And when it's attached to the vibrating base, this whole thing will vibrate. And the reason why we are interested in this type of structure is because they are known to exhibit band gaps and local resonances. Band gap means that if we measure a displacement of this point, the relative displacement to the base, then at some frequencies, this part will not vibrate. That means the main beams will not vibrate, but the small masses on the beam, they will vibrate, and they will create a local resonance. And in this case, it is reported in the literature that we should expect some higher energy production. So, but what about sensing? We are expecting that this type of structures will be also very efficient for sensing, because if we manage to measure voltage signal not from one, but from many, many cells that we have in this structure, then we will have all this additional information to sense the environment, to acquire information about the source of vibration, like traffic. And and that's our ultimate goal. So what we want to do, we want to design this type of structure and explore how they work for maximum energy production and maximum sensing accuracy. I have to confess, we are not quite there yet. So today I will be mostly talking about all the tools that we have developed for this problem. Starting with the numerical modeling of piezoelectric energy harvesters. Here we are using Kirchhoff-Love plate model with the Nietzsche method for the multi-patch coupling in the isogeometric analysis. So we do the discretization with the IGA. And then for the sensing, then we couple it with the optimization algorithm to optimize the energy production. And we did two types of study here. The first one was the standard optimization for the harmonic inputs. And the second one, we did optimization for the real application, for the real bridge that we have access to. And then I will introduce what we do for sensing. We developed a deep learning image-based framework for traffic characterization from the voltage signal. And then in the end, even though for some simple cases, but we managed to combine these two objectives and do this bi-objective design optimization. And unfortunately, it turned out that we cannot maximize both objectives at the same time. We ended up with a Pareto front, but I will show that a bit later. So here are all the equations for this model, the basic model that we use. It's based on the assumptions of the Kirchhoff-Love plate theory with only one vertical displacement. We can express all strains, stresses, and substitute everything into the that was for the substructure level layer. For the piezoelectric layer, we have additional electrical components in these constitutive equations for the stresses and electric field and displacements. So then we have to substitute everything into the Hamilton principle, all the variations of kinetic energy, elastic potential energy, electrical energy, and the work done by forces. And then, after taking this variation, we arrive to the weak form of the problem that now we have to discretize. And in this work, we're using isogeometric analysis. It's a variation of the finite element method that uses the same basis functions which are used in computer-aided design analysis, B-splines and NURBS. So it provides a tight link between design and analysis. The geometry is always exact. So here is actually a list of very standard features of the IGA. We have a better accuracy due to the higher shape functions. And particularly for the optimization problem, it's very convenient because the control points which are used for the description of the geometry, they can be used for optimization. It means that we can have this very nice parameterized shapes of the plate. So here's the mathematical expression of the B-splines as piecewise polynomials. So the basis looks something like this. We can have a rational version if we add the weights. And then if we need to parameterize the curve, we need a set of control points. So if we move these control points, the shape will change. That can be easily extended to 2D by doing a tensor product of one-dimensional shape functions. And then with all these control points, we can model much more complex geometries that we have here. So then we take this discretization, put it in the weak form, and arrive to this coupled system of the equations for the displacement and the voltage. So here I have expressions for all the matrices, for the mass stiffness and the linear damping model that we are using. And okay, this is the electromechanical coupling vector and force vector and some other notations which are used in these expressions. Then if we have a linear system and if we have harmonic input acceleration, we can derive the solution in terms of the voltage frequency response function that shows the amplitude of the produced voltage for any input frequency. And if we integrate that over time, we can quantify the energy which is produced by this system. We did a lot of studies on this very simple model. This is one particular example of how it was validated by comparing with the experimental data. So the model works very well. However, one of the drawbacks of IGA is when it comes to the creating complex geometries, we need to couple different patches, and that means we need to impose connectivity conditions along the boundaries. For this, we are using Nietzsche's method, which requires all these additional penalty terms along the boundary for the jump in forces, like the average jump in forces and moments and the displacement. But that we also implemented, that works quite well. The easiest way to validate the implementation is to compare with the one-patch model, which we just split it in different ways for two and multiple patches. And then if we look at the resulting FRFs, so they work quite well. So we are happy with the results. So now, then we looked at this more complicated system with the beam and the resonators attached to it. That's what we can observe.
So the electric circuits are not interconnected. Each patch sees only one electric circuit.
It can be one or it can be many. So in this one, it's a separate one for each.
Okay.
Yeah. And so now, if we look at the displacement of this tip for different input frequencies, that's a typical band gap that we observed. We observed at these frequencies. So we see that the main beam does not vibrate. The comparison between our model and experimental data, I'm not very happy with that yet. I think it comes from not properly matching the material parameters, so we are still trying to improve this. But at least we can clearly see the band gap. And what is also interesting, if you look at the different resonator, we see that we can harvest much more energy at lower frequencies. So if we add this effect from all resonators, we see that here, just before the band gap, we have all these peaks in the produced voltage, which is very convenient because then we can move to this lower frequency range and we can try to optimize this structure in the way that it's most efficient at the frequencies that we want. And those frequencies usually come from the application. So we did a lot of studies with this model. This one particular from our early work that I like the most is the shape optimization for two objectives. And here it's a simple harmonic input, and we look at the maximum of the produced voltage. We can see that the two objectives that we are using here, either the peak of voltage or the voltage per area, they are competing with each other, so we get a Pareto front. However, we are most interested in the optimization for the real working condition, and we are lucky enough, and we are very lucky because we have access to this particular bridge in New South Wales, Australia, which is equipped with a set of sensors. There are 24 sensors which were installed in 2016, if I remember correctly. But they constantly record acceleration. And that's how acceleration looks like. So you can see, well, you can tell me what the peaks are. These are the, this is the traffic, exactly. So this is a vehicle passing over the bridge. And if we don't have any vehicles, this is the ambient vibration history. So a typical event looks like this with a peak. And we can use this input, we can put it into the model that we have and estimate the amount of energy which is produced by one particular event. But then, of course, you will tell me, so, but it's just one event. Maybe if we consider a different event, the optimization results will be different. So how can we make sure that we find indeed the most optimal device for this bridge? So we did such optimization on a very large number of events, and then we clustered them, actually. We saw that there are 7 clusters, there are 7 devices that can be optimal, that can be considered as optimal. And then we did some comparison of how they perform for the 24-hour signal. Here's a very interesting result that the device which was optimal for the events, no, for the vibration windows without any events turned out to perform almost as well as the most optimal one. We did a lot of studies. Here's just one particular result for this case.
I'm sorry, I don't want to disturb you, but I want to understand. Optimizing means choosing what?
In this case, for this particular case, the geometry is simple. It's a rectangular plate where we optimize different combinations of length, thickness, and the coverage by the piezoelectric layer. So far we are working with this simple rectangular design. And then we couple it.
And each piezoelectric layer is connected one.
So now we only have one. There is one patch, one voltage, one produced voltage.
Okay.
Yeah. And I didn't mention, but the optimization method that we use is particle swarm optimization. Like I said, we did a lot of studies for this bridge. We looked at harvesters at different locations. We looked at the dependence on traffic. That one is particularly my favorite picture, where it shows all the voltage collected during the different time of the day. You can say that this is night, this is day, where there are more cars. And another interesting result that I wanted to show is here, where we took a similar study from a paper where they studied a different bridge. It was a train bridge with many train passages that they used. And the design that they proposed was based on this conventional approach of matching the first frequency to the frequency of the bridge. So we changed that. First of all, we showed that for the parameters that was proposed, first of all, our model produced very similar energy for the same design. However, if we do a proper optimization following a routine that we suggested, then we can increase the amount of energy by, I don't know, 18 times, if I look at these numbers, right? So here's what is concerned with the energy optimization. We have this model. It can be used for multi-path geometries. It can be paired with the design optimization algorithm. It can be paired with the real field data. And then we can do different kind of optimizations. So what about sensing? Now let's look at the inverse problem. So this time we will have a signal, the voltage signal, and the task is to find the parameters of the vehicle that produce that signal. In addition to the acceleration database that we have from this bridge, we have the strain data. And that strain data is linked to the speed. For each event, if we have the corresponding strain, we can estimate the speed. And that means we can label each event according to the speed. So we took our database and we split it into 3 labels for 30, 40, and 50 kilometers. And then we decided that we can use the image-based classification based on CWT transform, continuous wavelet transform. And for this particular event, the CWT image would look something like this. And then we can train the neural network to label these images. If we have the ground truth, if we have the database where we know which labels correspond to which images, we can train the neural network. And here we are using this very standard AlexNet. Here is the workflow, which I basically just explained. From this database, based on the strain, we can create labels. Then we can use these labels to train the network, and then we can validate it. So here is the architecture of the AlexNet. We tried the different ones, the different networks. They all performed quite similarly. That's the convergence plot. The accuracy that we get for the base case. So now we are working with acceleration, no voltage yet, just the acceleration. So the accuracy that we have is around 94%, which is good. But now, if we want to use voltage instead of acceleration, then different devices will produce different signals, right? If we look at this plot, so here we have 6 rectangular devices with fixed width, but we slightly vary the length. So we take 6 different values for the length, and if you use this device to convert the same event into voltage, you see that all these CWT images for voltage will look quite different. And that means that the sensing accuracy will be also different. And the energy produced by these devices will be also different. So this is the plot of the energy for all the configurations. And that's the plot for accuracy. We can clearly see that accuracy depends on the geometry and the energy depends on the geometry. So that means that if we do a proper optimization with these 2 objectives, we can see how these 2 objectives are related. Again, here we are in a very simple case of the rectangular plates, where we either use length or length and width at the design optimization problem, and we can either set up objectives with respect to energy and sensing accuracy, or we can divide energy by area. It's a very computationally expensive task, because for each configuration of the device, we need to train a new network. We have to estimate a new accuracy. So here we use the region meta model to help with these simulations. And if we look at the 2 objectives simultaneously, again we have something that looks like a Pareto front, where we see that if we want to gain a lot of accuracy, we have to sacrifice a little bit of sensing to gain more energy. Or if we want to gain a bit more of sensing accuracy, then again we have to sacrifice a lot of energy production. So I have to mention some limitations of all this. Of course, the computational cost is quite high. So far we have worked with only very simple geometries, but still computationally it's very expensive, because for each new design we have to train a new network, we have to estimate a new sensing accuracy. Another problem is that the results that we present, they are problem dependent. Everything that we have done with respect to this particular bridge. So if we change the bridge, of course, all designs will be different. And we don't know yet if it's possible to do some transfer learning transfer, or anything like this. So, and the third problem is that we have a lot of parameters that we need to tune, even in the sensing part, even for the CWT images, its accuracy and performance will depend on the corresponding parameters. So, and that's what we are doing right now. So we are working on looking into that metastructure that I presented in the beginning. And the model that I presented was linear, but it's of much more interest to include non-linearity when we are not limited only by the resonance. And we have our own experimental setup that we use to do some experiments and see how these models perform in the real life. Here are the list of papers that contain the results of what I just presented, with this one being published, being accepted just 1 hour ago. So this morning I received an email. So it's accepted, it needs to be changed. Yeah?
Congratulations.
Okay.